Okay, so let me see if the previous class is appearing here. I've saved it. I think only till here. Last class data didn't get saved, I suppose. Okay, this was much previous class to that. Okay, no problem. What to do? Fine. So yesterday's class, I think relationship of DFT with other transforms we were doing. So let us do this now. Relationship of Fourier transform of a periodic sequence of an aperiodic sequence. Okay, that means the relationship between DFT and DTFT. Okay, so you can write down, all of you write down a small introduction like, if x of n is an aperiodic finite energy sequence, is an aperiodic finite energy sequence with Fourier transform capital X of omega. Okay, capital X of omega. So this is the Fourier transform. That means only the time domain we have sampled. Frequency domain there is no sampling. That means the DTFT, Fourier transform means X of omega is sampled at capital N equally spaced frequencies as omega k is equal to 2 pi k by n, where k equal to 0, 1, all these until n minus 1. Okay, that means to say that your x of k, your DFT, you can say is x of omega sampled at omega is equal to 2 pi by n into k. Is it not? So basically you can say that a Fourier transform means what? Your time domain, you remember you had your time domain signal x of t. You will, for the ease of calculation, you will convert it into discrete x of n. This x of n, you will go in your frequency domain, that is your x of omega. So here what happens, frequency domain means you will do your Fourier transform and x of omega you got. So once you have come to your frequency domain and you have a continuous spectrum of your signal, suppose your x of n is something like this. We take another color. Okay, x of n is something, samples like this of different lengths. Something like this is your x of n. Okay, your x of omega, this is your n time. This is the amplitude values. So your x of omega, if you are plotting in the same way, this is continuous again. You will get, if you have observed, even in MATLAB you have the option to do your frequency spectrum. That means what? This time domain signal that you are having, you have got a set of frequency spectrum values like this, which is continuous with respect to frequency. This is continuous. So this is nothing but your Fourier transform alone. Okay. Now you are not interested. What you are going to do? This Fourier spectrum, I have explained this initially also when we did the sampling part. This spectrum, what you are doing with an interval of 2 pi by n each. Okay, you're sampling the frequency domain signal also, and with an integral multiple k, where this k index is going to vary from some 0 to n minus 1, where n is the length of the window that you're going to choose. That is actually your Fourier transform. The length of the window means you're taking this Fourier frequency domain signal, and what you're going to do, is,
Ma'am,
yes,
x of omega again we are sampling, ma'am.
no, x of omega, this is x of omega, right? You're,
Yes, ma'am. Continuous signal.
in the frequency domain, you have not taken discrete values. When does this become x of k? I'm showing you the transition from x of omega to x of k, how it happens. That is what we have seen initially, right? The same thing I'm repeating
Yes,
so
ma'am.
that you understand. So these
Yes, ma'am.
sample values has a length of 2 pi by n. This is continuous value. This you want to discretize it. You want to convert it into k in terms of x of k. X of k is actually what? This is actually 2 pi by n into k value, right? In short, you are writing x of k. So how that is written, I am showing you, that's all, so that you understand. So once you have sampled in the frequency domain, what is this until length of n minus 1 means a particular window you are using of a length 0 to n minus 1. So within this range also the sample length will be until n, because frequency spectrum signal may have, if it is a very random signal, okay, real signals are mostly random signals, real life signals like speech signal and all, it will have so many frequency components which you may not be able to represent in one go. So what you will do? You will use a window, you will show it in windows like this. So the actually this n value represent the length of the window you're going to choose, because or sometimes what happens, this entire thing you can take it as n. So that depends on the signal. Okay, let me not confuse you too much with that. Only thing is the range of values to which you're going to consider the k value is capital N. For the ease of calculation, we are taking it that way. Have you got it till here? All of you? So if you have understood this, it's very simple. What I'll write it in the notation also, you will understand. Okay, so let me clear this. Okay, so if you understood that, what is the meaning of this? X of k, that is the sampled frequency domain values, is nothing but x of omega. This is continuous value. So this continuous value, you are sampling with the rate of 2 pi by n into k. That is the meaning of this. Okay. Okay. In that case, how do you, also you should mention this k equal to 0 to n minus 1. Okay. Then what exactly is your x of omega? If you have to do the sampling, you need to know this, right? So this is nothing but means a simple Fourier transform. So you will take an infinitely long signal like this, minus infinity to infinity, x of n e power minus j omega n. This is your frequency domain signal, continuous frequency domain signal, or your Fourier transform signal. Also the inverse transform, how do you write it? X of n is given by 1 by 2 pi integral, because it is periodic with the pulse, we consider it to be periodic in nature. Okay, we want to, the very basic nature of your Fourier transform is to extract the hidden periodicity within the signal. So you will consider the range minus pi to pi x of omega e power j omega n d omega. Okay, so this is your discrete time signal. This is your time domain signal. This is your continuous frequency domain signal. Okay, in the side you can write it in bracket, so that just for your understanding. Okay, got it? So from this x of omega, what do I need? From this x of omega, What do I want? From this, I want to get x of k. So you know you have to sample it this way. So let us write x of k is equal to x of omega at omega equal to 2 pi k by n. So let us write this in terms of this. We are going to write this particular thing. This one we will substitute this way. Okay. So how can I write? You can write a sentence here. X of k is DFT, discrete Fourier transform, coefficients of a periodic sequence. Okay. Sequence. Say the periodic sequence you define as xp of n, for example. Okay, just to show that it is periodic. See, initially I told you we are taking an aperiodic sequence. Even if the sequence is not aperiodic, there is no periodicity within that. Okay, the DFT we are defining it always for a periodic sequence. We assume some periodicity is there. Alright. So xp of n, in the initial class if you remember, xp of n, the periodic signal, periodic means what? Say you take a range some L equal to minus infinity to infinity, okay, periodic with at any instant whenever you pick the signal. What is the meaning of this I will tell you. Suppose this is the number line, a particular signal, say the signal is like this, okay, this is your x of n, okay, maybe this is your total length of the signal is n. So if the signal is a periodic signal, okay, these values will go on like this. The same thing will keep on repeating, right? So whether you take it at this point or you take it at this point, arbitrarily some value L you are taking, so that what happens? Anywhere in the number line you shift L into capital N, okay, so say n is the index, say n is the index you are using, say n equal to 0, this is n equal to 0, from this value anywhere you are going to shift it, whether it is this side or this side, however you shift this particular signal, if it's a periodic signal, only one of these if you consider it is sufficient. So in general you can write it this way. Got it?
Yes, ma'am.
All right.
Ma'am, that n minus ln, how I got, ma'am?
See, this is a periodic shift in the signal. N minus means what? N minus ln is equal to 0, right? So L into N is equal to N. Is it not? So what is your N? Capital N is equal to small n by L. Some arbitrary value you are shifting this L somewhere. Or you see this way. Consider this as an integral multiple of L. Say it is substitute some value n minus give some 2 times n. Means what? Where does it go in the number line? Somewhere, suppose this is your n equal to 0 you are considering the signal. Okay. Where does it go? 2 times capital N means where is it going to go? The total length is going to be n. So it is going to be shifted by a value each sample from here. That means n equal to 0 to some 5, say 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 4 values are there. So all these 4 values, the entire value has a length of 5, that is 5 samples, are going to be shifted by, this is n, suppose it is 5, n minus 10. So whatever is there at n equal to 0 is going to be shifted where? At n equal to 10. That means after, suppose there are 5 samples, whatever is here at the 10th position, the same thing will repeat. Got it? You put some values here and you analyze, you will understand. Got it?
Yes, ma'am.
Okay. So basically you are saying that the signal is periodic. If it's a periodic, wherever you shift it, if you consider, in general you can write it like this. That means you take one particular signal, periodic signal, and you analyze it, you will understand. Okay, write down next. Finite duration sequence, the finite duration sequence, finite duration sequence, say you call x hat of n, is xp of n for a range of n minus 1. What is the meaning of this is, see this one, you are going to consider only this value 0 to n minus 1 set of samples. Somebody is waiting. Alright, got this? It means though the signal is, this is xp of n, continuously it is periodic, but this particular sample you are considering it as x hat of n. That's all. Here, right? And it is 0 otherwise. So you can also write x of n, the original signal that you are taking into consideration, which is the original signal which you are taking into consideration here for calculating your this one, this signal x of n. This is your signal you are considering, right? So how can you write that signal in terms of x hat of n? Oh, sorry. You can say that signal x of n is same as your x hat of n. Can I say this? Because I am always considering just for a periodic sequence, I am just going to consider from 0 to n minus 1. Even x of n is same thing. X of n also you are considering only from 0 to n minus 1. Right? Provided n is greater than or equal to some capital L length. This length is that of x hat of n. That means the n value should be a sufficiently large value. That's all. So if x of n is same as x hat of n, then you can definitely write your x of k as summation n equal to 0 to n minus 1 x of n. What is that equation that you have for x of omega? You have x of n e power minus j omega. I'll rewrite the equation here in the side. X of omega, what did you have? Equal to minus n equal to minus infinity.
E power minus j omega n, ma'am.
X of n e power minus j omega n. This was the initial equation you wrote, right? So from this equation, I'm telling you how we change the limit from this one. This is what I'm trying to tell you. See this. Minus infinity to plus infinity, your limit has changed. How it has become from 0 to n minus 1. Why we are taking that? That is because of this step. And what is happening in this step? We are taking only the one particular periodic set of values. That is why we can change the limit here from 0 to n minus 1, and instead of writing e power minus j omega n, we already know we have to sample it. So how will I write it? I will write it as x of n e power minus j 2 pi by n into nk, so that your k varies in this range only. Got this? See, you should each step, maybe in short, in one line, if I tell you what is this derivation, it is very simple. It is nothing but x of omega. You know the equation for x of omega. Omega is evaluated at 2 pi by n into nk, n into k. Okay. In short, in one line, if I tell you, this is the actual entire derivation. But how it has come? Okay, you need to analyze each step. You need to write few sentences. You should write it is periodic. You should write why it is periodic, how you are going to change the limit. All these things you should understand. Don't think it is just 3-4 equations by heart and write it. Don't assume like that. Okay. Okay, please try to understand why I have changed this, what is happening. Okay, so that things will be clear to you and it will not look like mere equations to you. All right. All right. So this is it. X of, you can write one sentence. Above equation DFT of x of n. Above equation DFT of x of n is a sampled version of its DTFT. Is a sampled version of its DTFT evaluated at omega is equal to 2 pi k by n. Okay. To recover the finite length sequence x of n, to recover the finite length sequence x of n. So, even in the sampling derivation you would have seen. Okay. You have two parts. What are those? One is your, from x of n, you go with x of omega, then you sample this again and you get x of k. Now what you should do, from this x of k, you should obtain back your x of n. Is it not? That means you should see your inverse DFT also. See the initial equation. Initially I made you write, remember? See this. Look at this equation. You have x of omega, you have x of n. X of omega you have found out how you will get x of k. You sample it at 2 pi by n into k, you will get this. How do you get x of n back? We will see that now. Okay. Okay, so what did you write? What did I say last?
To recover.
Yeah, to recover the finite length sequence x of n. To recover the finite length sequence x of n, you need to recover your x of n, right? Recover x of n from n samples. What are these n samples that you are considering? The frequency domain values. The DFT spectrum corresponds to 0 less than or equal to omega less than or equal to 2 pi. That means you have to get back your x of n. From the graph you know that x of n is the value, you are considering only the periodic value. So if it is a periodic value in your frequency domain, the range of frequencies will definitely vary from 0 to 2 pi, that's it. That is the reason you are writing the range like this, okay? 0 to 2 pi and is plotted at frequencies omega is equal to 2 pi k by n. This I showed you, right? You are going to plot this. You have your x of n value. I erased it, right? I think I erased it. Okay. People are waiting. Why do people join so late? Okay. All right. So this I think I showed you this. You have the frequency spectrum. You will have the frequency spectrum something like this. You are going to do what? Sample it at how do you do the sampling in the frequency domain? This is omega. This is your frequency x of omega. How are you sampling it? What is the length of each of this? This is
Ma'am, k value we are giving 0, 1, 2, 3 up till
yeah.
n minus 1, ma'am.
Yeah, k equal to 0 to n minus 1 you are going to take, and this is 2 pi by n into k value. Each of this width of this samples, between the samples will be 2 pi by n, multiples of k we are going to take, isn't it? This is what we have written. So whatever you wrote earlier, the meaning of that is this. Okay. Okay. So to recover the finite length sequence x of n from n samples of k, What are you going to write down? It is plotted at frequencies omega is equal to 2 pi k by n. I hope you have written till here. Next sentence you write, to recover the finite length sequence x of n from capital N samples of x of k, capital N samples of x of k, we use d of omega d of omega is equal to 2 pi by n and omega is equal to 2 pi k by n. Where are we going to use this? We'll use it in your x of n equation. Recall your x of n, your inverse value. X of n, how do you do?
Ma'am, can you say the statement once
Formula
again?
we have integration formula, ma'am. 1 by pi, 1 by 2 pi minus pi to pi x of omega e power j omega n d omega.
Exactly. So instead of what is the meaning of this particular line is that you are going to replace that omega and you are going to write it in terms of x of k. So whenever x of k is going to come into picture, you will not use integral because it is not continuous. You will use summation. Got it? Whenever things are not continuous in nature, you cannot use integral. So instead, what are you going to use? You will use summation. Since it is a periodic signal, even the inverse transform, what we are going to do is, we will write this like this, integral 1 by 2 pi, summation, k varies, you have fixed the range of k. What it is? You know k is varying from 0 to n minus 1. Next is x of k. Since you are doing the sampling, e power minus j omega n. How are you going to replace that?
2 pi by k into n.
Yeah, so this is not minus, plus, right?
2 pi.
E power j into 2 pi by n into nk. You have d omega also. So what do you do for the d omega? D omega is replaced by 2 pi by n. So if you are getting confused here, I'll rewrite the earlier equation. Your x of n initially is 1 by 2 pi integral continuously, because this is continuous, right? Minus pi to pi you had restricted it, x of omega e power j omega n d omega. So in this equation you are doing these changes. And because you have discretized this x of omega, you have evaluated at omega is equal to 2 pi by n into k values, you have sampled it, this becomes summation. Hope you have got it.
Now we can take 2 pi by n outside the summation, no, ma'am.
Yeah, you can take 2 pi by n, that's what you should do actually.
Yes, ma'am.
Good. What is this? Okay. So what will you get? You remove this 2 pi by n into n outside. So what are you going to get? 1 by n, 2 pi will go. Summation k equal to 0 to n minus 1 x of k e power j 2 pi by n into nk. Have you got this? So what can you tell about this equation? Do you remember what is this equation? What is this equation?
For Fourier coefficient, we used to write 1 by n, ma'am.
Fourier?
Ck for that.
No.
Ck.
You recall. See this. This is the equation for your IDFT, right? Inverse discrete Fourier transform. Yes or no? DFT is x of k is summation n varying from 0 to n minus 1 x of n wn power nk. Wn is e power minus. Here e power plus is there. This is wn power minus nk x of k 1 by n. Is it not your IDFT equation?
Yes, ma'am.
This is your IDFT equation.
In place of omega n power minus nk, we have e power j 2 pi by n into nk, ma'am.
That's all. Wn power minus nk. Correct? This is your IDFT equation. So write down. This is inverse discrete Fourier transform. periodicity of x of n, sorry, periodicity of IDFT implies that x of n corresponds to one period of a periodic signal. That is why we are restricting our, instead of taking n from minus infinity to plus infinity, it goes to 0 to n minus 1 because it is periodic. That is why omega, you have a different set of values. You have sampled at 2 pi by n into k values, and k you are taking from 0 to n minus 1 k values. Okay, got this? Is very important, because we are able to get a finite range for your small n and small k. We are able to analyze the signal easily. Or else, if it is continuous both in time and frequency, what will happen? You are not able to analyze anything. So that is the relation between your DTFT and DFT. What is that? DFT, you are taking x of k. DTFT is nothing but x of omega. DTFT, inverse discrete time Fourier transform, means you will get your, here also you will get your x of n back because time already. Here also you will get your x of n back. Only thing is, here in your IDFT, when you have to get back, this is an integral. In this case, when you have to get back, it is a summation. Got it? Got this? Because you cannot, if this is discrete in nature, you cannot do integration. Since this is continuous in nature, the inverse of that you can use integral. All right. I hope you will, somewhere in the side you write down this so that it's easy for you to understand. All right. Hope all of you have written it down. Okay. Meanwhile, as you write it down, you answer your attendance. Deepak Kumar. Okay, let me call out your USN. 18 EC 44. 1. Okay. Adarsh 02.
Present, ma'am.
Adanika Dharmik Sai 3. 03. Absent. 04. Akash. 05.
Present, ma'am. Akash.
Akash present. 6. Ananya.
Present.
7.
Present, ma'am.
8.
Present, ma'am.
9.
Present, ma'am.
10.
Present, ma'am.
11. 11. So is that? 12.
Present, ma'am.
13.
Present, ma'am.
Please switch off your, who is that? Kusuma Sagar.
Yes, ma'am.
Please switch off. Who is that making noise? $14.
Present, ma'am.
15.
Present, ma'am.
16.
Present, ma'am.
17. 18. Chandrasekhar. 19. 20.
20 present, ma'am.
21.
Present, ma'am.
22.
Present, ma'am.
23.
Present, ma'am.
24. 25. 26. 27. 28.
Present, ma'am.
29. These 26, 27 and all are not attending classes or what? 29. 29 is present? No. 30.
Present, ma'am.
31. 32.
Present, ma'am.
33. 33. 34. 34. Let me do the next one. Then I will take attendance. Okay. Next is relationship to Z transform. Okay. We have all finished writing. Okay. Write down. Double-sided Z transform of a sequence x of n. Double-sided Z transform of a sequence x of n is given by x of n. This is a sequence. Double-sided Z transform of this x of n is given by summation n equal to minus infinity to infinity x of n z bar minus n. Okay. With an ROC, ROC means region of convergence. That includes the unit circle. Means you have the unit circle. So your region of convergence should include this unit circle also. Real and imaginary. This is how it is. If x of z is sampled at n equally spaced at n equally spaced points on the unit circle zk, small zk, you write down, is e power j 2 pi by n into k. That means you have your x of z. So if the meeting is ending, please join after 5 minutes, okay? As soon as it ends, please join back.
Ma'am, what is that statement, ma'am? If x of z is sampled at?
Capital N equally spaced points on the unit circle. See, that means on the unit circle, you're having this represent your Z transform. If you're going to sample this at n equally spaced values, okay, with equal distance, you're going to sample each of these. So what is the meaning of this? This is on the unit circle, you will evaluate it such that your Z is equal to e power j 2 pi by n into k. That is the meaning. Zk you write because you are introducing the constant value, integral value, integers, k value. So write down zk is equal to so much. So you can write it in such a way that x of z is evaluated at z is equal to e power j 2 pi by n. This is the way to represent it. Okay. So write down that equation. Substitute this in your equation there. In your equation 1. Substitute it. What happens? X of z is nothing but x of n summation n equal to minus infinity to infinity x of n. Instead of z, you will write e power minus j 2 pi by n into k is also there, n is also there, n into k. Minus sign is already there here, right? So you are evaluating at z is equal to exponential. You are replacing z with exponential value. So you got this expression. See, in every derivation, your ultimate aim is from the respective transform, you have to obtain your DFT. Your final equation should be DFT. So that what all you can do to do that, that all we will do. All those things we will try to do it. So here, it's our aim to, from the Z transform, we want to find out the relation with respect to DFT. You know, in DFT equation, exponential term has to be there. So what will happen if you evaluate your Z, x of Z at values of exponential, in terms of your exponential, you will be able to get your relation with respect to DFT. So that's what we are doing. Okay, after writing this, write down. If the sequence x of n has a finite duration of length capital N, if the sequence x of n has a finite duration of length capital N, or less, the sequence can be, just a minute. See, for the next class, I have shared the Google Meet link for HOD Sir's class. Okay, it's there in the class group. You can join it after my class. Once I stop,